This theorem says that every m by n matrix like A is row equivalent to a row reduced echelon matrix. But how is going to help us to solve a system of linear equations? To solve a system of linear equations using Gaussian elimination with back substitution, first write the augmented matrix which is associated to your system of linear equations. Then use elementary row operations back and forth to rewrite the matrix in row echelon form. And finally, write the system of linear equations that is correspond to the matrix in row echelon form. Then use back substitution and solve the system of linear equations. For example, let's take a look at one example from Larson book. In this system of linear equations, you have 1, 2, 3, 4 equations with 4 variables. The augmented matrix for this system is going to be 0 because you don't have any x1 here. It means that originally it was 0 times x1. So the leading coefficient for the first row is 0 for now. So you have 0, then you have 1 times x2, 1 times x3, negative 2x4 equals to the constant term negative 3. Then we jump into the second row. The second row starts with 1 times x1. So 1, then 2, negative 2, 0, and 2. Finally, the third row, you have 2, 4, 1, negative 3, negative 2. And the last row gives us 1, negative 4, negative 7, negative 1, and negative 19. This is our augmented matrix. Now we're going to apply some elementary row operations to rewrite this system in row echelon form. Take a look. The leading coefficient is 0 here. But on the second row, the leading coefficient is 1. So remember that we can always interchange these two rows. Or you might say, hey, why we don't interchange the first row and the last row? Why not? You can do that. There is no unique way. For simplicity, just interchange the first two rows. What are we going to do next? We're going to get rid of these 2. How you can do that? You can multiply the first row by negative 2 and add it to the third row. So negative 2 times the first row and adding that to the third row. Let us do the algebra. Negative 2 times 1, negative 2, negative 2 times 2, negative 4, negative 2 times negative 1 gives us 2, negative 2 times 0 is 0, negative 2 times 4 is negative 4. Then we're going to add that to the third row, which is just right here. 2, 4, 1, negative 3, negative 2. So if you add these together, these two disappear, 0. So the coefficient of x becomes 0, the coefficient of y becomes 0, the coefficient of z is 3, and the coefficient of the fourth variable, which is denoted by x of 4, is negative 3. And then the constant term becomes negative 6. So as you can see, it is just right here. This is the algebra behind it. Now what? So take a look. I have the leading coefficient 1, and the entries behind it are 0, then 0, but I have a 1 here. I want to get rid of this 1. What you can do, you can multiply the first row by negative 1 and add it to the last row. What's the algebra behind it? Negative 1, negative 2, 1, 0, and negative 2 added to the last row, 1, negative 4, negative 7, negative 1, and negative 19. It gives you 0, negative 6, negative 6, negative 1, and negative 21, which is basically this new fourth row down here for you. Okay. So far, we created 1, and below 1, we have 0 entries. We're happy here. We're going to jump into the second column. Take a look at the second column. I have a 1 here, which is nice. But below 1, I need to have zeros. And if I can make above 1, the entry 2 becomes 0, it would be much more nicer. But let us do that. You see, this entry is equal to 0. We just need to get rid of negative 6. So multiply the second row by 6 and add it to the last row. It creates 0 for us. and then another 0, it becomes negative 13, and here you get negative 2 and 1, which is negative 39. Now what? I go to the next column, column 3. As you can see, the entry on the main diagonal is 1. Below 1, I have a 0, right? What we did, we just divide this guy by 3. Divided the third row by 3. So it became 0, 0, 1, negative 1, negative 2. And below 1, you have a 0. So take a look. Elements on the main diagonal for this part of the matrix, if you want to take a look at it, the coefficient matrix, they are all 1. And below the main diagonal, you have 0. Again, what you could do, you could just add the second row by negative 2 and add it to the first row, and multiply the third row by negative 1 and add it to the second row, and just add the first row and the third row, and this guy becomes 0 as well. So you could go into the next step, but you can stop at this point. The system correspond to this matrix is 1 times x1 plus 2 times x2 minus 1x3 plus 0x4 equals to 2. From the second row, you get 0x1, 1x2 plus 1x3 minus 2x4 equals to negative 3. And from the third row, you have 0x1 plus 0x2 plus 1x3 minus x4 equals to negative 2, which is basically here. And from the fourth row, you have 1 times x4 equals to 3. So now by using back substitution, since x4 is equal to 3, you can substitute this guy here to find your x3. x3 becomes 1. And now that you have x4 and x3, you can easily calculate x2. x2 becomes 2. And finally, if you plug in everything in the first equation, x1 becomes negative 1. So this system, the original system, is consistent with one unique solution.